Okay, so now we're back on to Google Chrome. We're looking online. These are all of the parameters that were given for this problem. And then we're specifically looking to simulate the concentration profile and the temperature profile when we change the cooling in like two different cases, changing from 300 Kelvin to 290 Kelvin, and then from 300 Kelvin to 305 Kelvin. So we're going to go into Python and see what we can do with that. So first, we're going to have to initialize some of our libraries. And then that's NumPy, that's our mathematical tool. To import solve IVP, that's going to be our numerical solver. And then this is for our plotting. So now what we're going to do is we're going to initialize all of our parameters that were given. So on my iPad here, I have all of them listed here so I can glance quickly. So our flow rate Q, like I said earlier, the flow rate going in is the same as the flow rate going out because it's an overflow situation. That is 100 liters per minute. The concentration of A going in is 1 unit of mole per liter. Our temperature going in is given to be 350 Kelvin. Our volume is constant at 100 liters. Our density of A is given to be 1,000 grams per liter. Our heat capacity is constant, and that's given at 0.239, and that's in units of joules per gram Kelvin. And add a decimal point to make these floats. Next, we have the negative heat of reaction is 5 e to the fourth. That's in units of joules per mole. Next is the coefficient E over R. We're just going to call that ER. That is 8,750. Unit of that is Kelvin. And then our P naught in the Arrhenius equation is 7.2 e to the 10th. And the units for that is the same as the unit for rate constant 1 over our time, in this case minutes. Our coefficient and the heat transfer rate, UA, that is given to us as 5 e to the fourth, and that's in units of joules per minute Kelvin. And then our we're gonna call the cooling temperature TC. We're gonna set that, since we're gonna start at 300, we're just gonna initialize that. And then actually no, we'll start at 290 and then kind of play around with that. And then some of our other initial conditions, the concentration coming in, or the initial concentration out is 0.5, that's in units of moles per liter. And then the initial temperature, T naught, is equal to 350 kelvins. So now that we have all of these, we can start writing a function. So we're going to define our function, RHS for right-hand side. We need some time, and then the vector v. We're going to unpack the vector. So we need concentration and temperature. V for the vector, capital V for volume, and then our equation for K, our Arrhenius equation. That's negative ER divided by T. And then now we can write our two differential equations. So dCA dt equals Q times the difference in concentrations divided by volume. And then we're also subtracting the rate constant times concentration. Let me make sure on my, yep, that matches with what we said earlier. And then dt is equal to 3 terms. So we have the flow rate Q multiplied by the difference in temperatures divided by volume, and we're subtracting UA divided by heat capacity multiplied by density multiplied by volume. So that's all in the denominator. Multiplying this by the difference in the temperature of the reactor and the cooling temperature. And then finally, we're subtracting the enthalpy term. So what that looks like is or we're adding because we're given the heat of reaction in terms of negative. So we're gonna do neg HR times our concentration times rate constant divided by heat capacity multiplied by density rho. So that should be all of that, and then we're going to return an array of these two. So that is our function, and now we're going to call this variable res for result, and then use solve IVP. Our function is right-hand side. We need to also give a time, so we're going to say t end equals 10 minutes because that is what is given in the problem. In the textbook, it shows the graphs and it uses in time of 10 minutes. So our time span here is going to be from 0 minutes to 10 minutes, or t end. Our initial conditions are C naught and T naught in that order, because that's how the order we have this vector unpacked. And then our method, we use Radu, and then make sure that our dense output is set to true so we can integrate this. So now we're going to start plotting. So to make our sort of arrays for the y-axis and x-axis in that case, t-plot, that's going to be our time plot, the x-axis. We're going to do evenly spaced from 0 to t end with 500 points. Our CA plot and T plot are going to be calling the solution of this solve IVP, and we're going to be using that T plot for the x values. We'll keep that separated. So we're going to make the plots now. We need to have, we're going to do one row with 2 columns. Add our first plot. In the first row, the first column, our x-axis is going to be the time plot, and then our y is going to be the concentration plot. And then we're going to just name this concentration of A in moles per liter. And then I'm going to copy and paste that similarly. For the second column, we're going to plot temperature plot. I'm just going to call it tank temp. Sure. We're going to update the layout. We're going to have the height be 1,000 pixels width. Or should I do it? No, I'll do it longer since there's 2 columns. And then the template we'll use poly dark. Preferred, just aesthetics reasons. So as you can see, when we set the cooling temperature starting at 290, that it does kind of reach this sort of steady state. And then so it's asking if we're increasing from 300 to 290. So let's see what that 300 looks like. 3,300. It gets up to around 0.88. The concentration of A kind of bounces up to around 324. So let's go back to 290. So the concentration, if we decrease the cooling temperature, it's going to increase our concentration and decrease ultimately the tank temperature. So that makes sense. And then let's say we're going up to 305. We're increasing the cooling temperature. We get this sort of oscillation, and we're not reaching a steady state here. However, if let's say we increase it just a little bit more, you can see that we do ultimately reach a new steady state around 0.1 for the concentration of A in moles per liter, and then a temperature of around 383 degrees Kelvin. So that's kind of our simulation of our concentration and temperature profiles, looking at a dynamical system for a CSTR with a cooling jacket as we're manipulating the difference in the cooling temperature. So yeah, thank you guys. Okay, hi everybody. My name is Connor Bush. This is homework 2, part C. I'm going to read our prompt as to what we need to be doing, and then I will get into deriving everything we need to on my iPad right here. So part C, derive the time-dependent material and energy balance equations of the CSTR described, and then we're going to code, solve, and plot the time-dependent concentration and temperature profiles for the CSTR with the given step changes in coolant temperature. So I can kind of explain what's going on here. Need to pull up here. Okay, so we have this continuously stirred tank reactor here. There's a cooling jacket marked by coolant temperature TC right here. There's this given flow rate coming in, the concentration coming in, the temperature coming in, and then the flow rate going out is the same as the flow rate going in. The concentration out is, since it is a stirred tank reactor, we are considering that it's perfectly mixed, so everything coming out is equal to what is inside of the reactor at the time. And then same with the temperature leaving. So here are some of the parameters that we're given. So we need to perform a mass and energy balance for this first order reaction. We're going from reactant A to product B. We're also told that it's exothermic. So if we look at a mass balance first, just to note, our concentration is given in moles per liter, so moles per unit volume. So if we multiply that by the volume, we get the change in moles with respect to time. So that is our mass balance. So we know that the flow rate coming in is in units of liters per minute. And then we ultimately want to get this in terms of moles per minute. So if we multiply by the concentration, we get moles per liter. Yep. So that cancels that out. So essentially we're just dealing with this. So what comes in it's the difference between what's coming in and what's going out. So the flow rate going out multiplied by the concentration going out. We know that the flow rate going in is equal to the flow rate going out. So we can simplify this further. We know that we're working at a constant volume batch reactor, so we can pull that outside of the differential. So we're just left with dCA dt equals Q CA in minus concentration out, or just CA. And then also we know that there's a reaction occurring, so we have to subtract some reaction term. We know for a first order reaction that we're working with the rate constant multiplied by concentration of the reactants Ca. And then in order to get K, we can call the Arrhenius equation here. So that is equal to this exponential factor multiplied by the exponential of the negative activation energy divided by the gas constant multiplied by the temperature. We're given E over R. So we can split that out later when we're going to code. But since the rate constant is positive, we're subtracting positive number. So it's just minus K Ca. And then if you recall, our units of concentration are in mole per liter per unit volume. And then our rate constant is 1 over minutes for a first order reaction. So we just have to multiply by volume to cancel out that volume term. And then if we simplify this further, we get that dCA dt equals sorry, this is very finicky. This flow rate Q over volume multiplied by concentration in, subtracted by the concentration out, and then minus our KCA term. So this is our temperature concentration differential from using mass balance. So now we want to do an energy balance. So essentially we just want this in units of joules per unit time. In this case, we're working in minutes. So to kind of get there, we are given the heat capacity in units of joules per gram Kelvin. So if you think, so joules per gram Kelvin, if we multiplied by density, that's grams per liter, cancels out the grams, multiplied by volume, gets rid of the liters. If we multiply by temperature, that gets rid of the temperature unit on the bottom. So we're just left with joules on top. And then on the bottom, it's just dt. So that's where we get our time factor. So we also know that the heat capacity, the density, and volume are all constant, so we can bring that outside of the differential. So we're left with this. And then similarly up here to the mass balance, we're working with flow rates. So Q, that's in moles per or liters per minute. And then if we multiply by heat capacity to get the joules, we're left here. Then we have to multiply by temperature, get rid of that term, multiply by density, gram per liter. And then we have our units of joules per minute that's our desired. So we can just easily the difference in temperature. So if we're multiplying we're just looking at the difference in temperature because that's the only thing changing. So we have Q, the flow rate times the heat capacity times the density multiplied by this difference of the temperature in minus the temperature out. Since we're looking at a jacketed reactor with some sort of coolant temperature, the rate of that can be expressed by this equation here, where the U is the heat transfer coefficient, A is the area of the reactor, T is the internal liquid temperature, and then the TC is the coolant temperature, and this is in joules per unit time. So this is positive. So we can subtract that out. So UA T minus TC. And then additionally, since there is a reaction occurring, we have to look at enthalpy. We're given the negative heat of reaction. That's in joules per mole. So if we multiplied that by our concentration, mole per liter, and then multiply that by volume, we're left with joules. And then if we multiply by the rate constant, that's 1 over minutes, because that's the units for a first order rate constant. So if we get all of this together, we're left with this expression in units of joules per minute. So we can subtract that, but since there's this negative sign, I'm going to add it. So we have negative heat of reaction multiplied by concentration, volume, and rate constant. So if we move all of these over to the right hand side to isolate dt, we're left with an expression that looks like this. So Q over the flow rate over the volume multiplied by the difference in the inlet and outlet temperature minus heat transfer coefficient multiplied by the area of the reactor divided by heat capacity, density, and volume multiplied by the difference in the reactor temperature and the coolant temperature. And then finally, the concentration times the rate constant divided by our heat capacity and density. And then this is multiplied by the negative heat of reaction. So this is our expression for the change in temperature with respect to time using an energy balance. So now what we're going to do is go into Python and get this coded so we can plot these expressions and change the coolant temperature just to see how that affects the dynamics of the system. So let's get into Python.